Okay, section 1.5 is about exponential functions, and to do that we're going to talk about exponential rules a little bit, kind of review some of those. So let's talk just a brief second about what an exponent is, right? An exponent is how many times a number is multiplied by itself. So an exponent of 2, like x squared, would mean that the number x is multiplied by itself twice. So you get x times x. 5 to the fourth, the number 5 is multiplied by itself 4 times, right? So exponents count things, and when we count things we can use our counting principles, right? So if I have an x number of a's here, and I'm going to multiply that by y number of a's here, well, really what I did was I multiplied a by itself x times and then by y times again, so x plus y times altogether, right? So there's one of our exponent rules. If you multiply two numbers with the same base and different exponents together, you add the exponents and put it on the original base. Same thing with division. Division is the opposite of multiplication, so we're taking away multiples when we divide. So a to the x over a to the y says I have x a's all together. I'm going to take away y of them by division. So what I'm left with is x minus y a's multiplied together. If I have a to the x to the y, so I have y copies of x copies of a. So I've got a whole bunch of copies of a. How many of them do I have? Well, I've got y times x of them because there are y groups of x copies. So altogether I have x, y, a's multiplied together. Another one that we have, if I have a to the x and I have a different number b to the x, well, because of the commutative property, even though all of the copies of a come first and then all of the copies of b come next, I could have written this as ab, dot dot dot, ab, where I have x pairs here, right? And so I could rewrite that as ab to the x. That's because we can use the commutative property. If for some reason I couldn't multiply a times b and get the same thing as b times a, that doesn't work anymore. And there are some mathematical places where that doesn't work. But with real numbers, works just fine. We can commute multiplication. Okay, similarly, division. If I have a over b and I've got xa's on top and xb's on the bottom, I could rewrite that as a over b to the x. Okay, so those are our basic exponent rules. And then that leads us into exponential functions. Exponential functions, remember we talked about in a video yesterday, was a function where the variable is in the exponent, right? In all of these, I've sort of got x's and y's in my exponent. Well, that's because I want to think of a as a fixed number at some point in time. And so I'm going to write down an exponential function. And sort of the most basic exponential function is f of x equals some constant times some base raised to the variable power. So this number, it should be non-zero. Probably doesn't want to be 1 either. And it should not be negative because remember, fractional exponents mean roots, and if I have a negative base here, bad things could happen with like square roots. If x was a half and I had a negative number down there, I'd have imaginary numbers. So I want a to be bigger than 0. Okay. I usually avoid 1 as well, because if a is 1, then this is just a constant function and there's not really a reason to write it like this. But technically you could write it like this. I probably wouldn't call it an exponential function, I'd probably just call it a constant function. So we probably want to avoid a not equal to 1 as well. Otherwise you just get f of x is equal to c. Okay. And this can be any number. Okay. And what do these kind of look like? Well, for c positive and a bigger than 1, which is kind of your common case, let's look at maybe say f of x equals 3 times 2 to the x. These graphs, well, they're going to start out at wherever that c value is on the y-axis. So in this case, c is at 3, so this is going to be at 0, 3. That's where it's going to start. And then if I go over 1, I have to go up 2 times as big. So it's at 3 here, so it's going to be at 6. If I go over 1 again, I'm going to have to go from 6 all the way up to 12. Right? I get another factor of this is 6, this is 6. I'm up to 12. So this is at 2, 12, this is at 1, 6, this is at 0, 3. If I go to the left 1, I have to be half as big. So this is going to be at minus 1, 3 halves. If I go to the left again, I'm going to be half as big. Right? I'm counting how many 2's I have. If I move to the left, I'm taking away factors of 2, so I get to be half as big. This is going to be minus 2, 1/4. And if I keep dividing by 2, I keep getting closer and closer to 0, but I never actually get there. And if I keep multiplying by 2, I keep getting really big really fast, right? So graphs of exponentials tend to have this shape, right? You have this shape where you go through some point on the x-axis, which is given to you basically by that c value. You get really close to 0 on the left, and you get really big on the right. Okay, there's your general shape of an exponential. If a is less than 1, so let's say this is a is bigger than 1, right? If a is less than 1, when you multiply by a number less than 1, things get smaller and smaller and smaller. So you still start here, but as you move to the right, you get smaller and smaller as you get close to 0, and then on the left, you shoot up towards infinity. So this is a is less than 1, but bigger than 0, because a can't be negative, we said. Okay, and this is always at 0, c. Okay, so you sort of have your point of origin. If you move to the right, you increase the number of factors of a that you have, so you either get bigger if a was bigger than 1, or you get smaller if a was less than 1, and vice versa if you move to the left. Okay, that's the exponential review. We're going to talk about inverse functions and logarithms and inverse trig functions next in chapter 1.6, section 1.6, and that'll be a little bit more in depth because those are some slightly harder topics. All right, I'll see you in 1.6.